I'm Tom Scott. This is Roman, who's now going to go and sit down for a minute. I'm jealous. So the first thing I've learned from today is we've got to change that title slide because it scares everybody away to the back. What's going on with the front two rows? That's crazy. But what we're going to do is we're going to talk about turning the database inside out again. And really the subtitle is very critical to this. We're going to ask, what if everything was Iceberg? So hands up if you've been doing Kafka or been aware of Kafka or Kafka-related things for more than a decade. I know. You were expecting me to say a year or 2 years, weren't you? No, a decade. If you had been doing it for a decade, you probably will have caught this talk. So Martin Kleppmann, legendary Oxford lecturer and writer of designing data-intensive applications. It's the Bible. It's about that thick if you ever come across it, but it's really good. Gave this talk more than a decade ago now, where he took the essentially opaque at the time concepts that make a traditional database system work and imagined what would happen if we were to take them and expose them publicly, make them systems in their own right, and then see what kind of architectures and what opportunities that would give us. You can tell how old it is from the font and the fact that it says Samza on it. Anyone remember Samza? Yeah, we're going back a long time for Samza. Yeah. But Martin's contention was that a traditional database system is made up of really four components. So at number one, we've got replication, we've got secondary indexing, caching, and materialized views. This all seems fine. I need to make a special clarification about Martin's definition of replication. When he's talking about replication, he's talking about a record of operations that have occurred on the database that is then shipped over to another instance to make sure that they are consistent for whatever reason. Now, I've gone a long way round the little word journey to say he's talking about Kafka. He's talking about logs, and that was the main contention of his talk. What if we took the replication mechanisms that you have in a traditional database and you expose them? And what you ended up with really was event streaming and stream processing. It's been a decade. I think we can agree that event streaming and stream processing have been quite successful. They've certainly done all right for me. But what about the others? Let's have a quick catch up and see where we went. So we said replication, we did really nicely. That's fantastic. A whole industry's grown up about it. Everybody loves Kappa architectures. We're all happy. And I think similarly with materialized views. If you have an event stream and you want to surface that to an application that is not used to consuming event streams and doesn't want to follow the consume-produce pattern, then a materialized view is really the way to go. And we'll stay with Martin and we'll use the most broad definitions of these so that a materialized view isn't necessarily just your state store in your Flink app. It can also count as the destination Postgres database that's at the end of your connector, or any other sort of downstream store where we're taking events, we're aggregating or updating them, and we're creating a very batch-like view that we can then consume in, I wanted to say more traditional, but not more traditional ways, in alternative ways. But what about numbers 2 and 3 there? How many of you guys are working on Kafka day to day? Do you know what? As a percentage, that's better than I normally get. So I'm quite happy with that. How many of you, any of you coming across secondary indexing in your day to day? Oh, that's quite like that one. How about caching? Yeah, a little bit. Yeah, so I think it's quite fair to say that the frowns are there because as a suite of components, it's only really replication and materialized views that have taken off and become the core pieces of architecture that we've turned inside out. This talk, we're going to look at why that is. We're going to look at some of the elements of and the mechanisms of a traditional database that have expanded a little bit in the last decade, and see whether we can't close those gaps. Now, I said at the beginning that this was a talk about turning the database inside out, but it had a special bent towards Iceberg. Why Iceberg? It's because I see Iceberg and Kafka as a standardization. There was a time many moons ago, where if you wanted to run an operational workload, you created a lot of point-to-point connections, a lot of fragile interfaces, and Kafka really came in as a standard and solved that problem. I believe, and I'm not the only one, that Iceberg is doing the same thing to the fragile point-to-point connections we have on the analytics side. And by that, I mean ETL. So Iceberg is providing this standard layer of high-volume analytical data that Kafka did for the operational realm. Now, once you have those two standards in place, you get some really, really interesting opportunities. So that set it up. Let's look at those mechanisms that I mentioned before. All of you that are familiar with database systems have probably encountered at least two, probably all three of these at some point in your life. We're going to revisit them with a bent towards Kafka and a bent towards Iceberg, and we're going to see how we can put them all together. So there's a lot more of this stuff that we can look at, but these ones fit quite nicely, and I've only got half an hour. So the first thing we're going to look at is long-term storage. Every database system you're going to see needs to store high volume of data, so needs some kind of persistent storage. We forget these days that Kafka wasn't designed with that in mind. We're also going to look at WALs. We're looking at write-ahead logs. We're going to look at stores of operations and whether they can be used for more than just the replication we spoke about in the earlier slide. And then finally, we're going to get onto my favorite subject. We're going to talk about a bit about indexing and performance improvements. So let's dive straight in. We'll take the easy one first. There's nothing really contentious about storing data for a long time. And I would have to say there's nothing really contentious about storing data for a long time in Iceberg. It's what it was designed for. It's really great at it. Kafka, however, was not. Kafka is from a pre-cloud world where what we did was we had co-located storage with the application, and we made the application responsible for replication. This is a well-practiced pattern, and it works great. But when you're trying to optimize for cloud costs and you're trying to minimize cross-AZ traffic and you're trying to do things like that, it becomes very, very painful very, very quickly. So I think the world needs to move on a little bit. Even more important in an operational environment is that this doesn't make scaling easy. Any of you that's ever added a broker to a Kafka cluster will know that before it can become useful, you've got to ship all the partitions over from this one to another one. If you had a better storage scheme, you could probably just make that instantly available. The good news is, it's not bad at it anymore. This is the biggest problem in Kafka, or it could arguably be said that this was the biggest problem in Kafka a year ago now, but yes, and there are many, many solutions to this problem, none of which I'm going to talk about today, because it's a whole different talk and a whole other subject. But if you want to store long-term data in Kafka, it's now very, very much a possibility. But none of them are using Iceberg today. And the question is, why not? We had the table format wars. Iceberg is the victor. It's the standard for long-term storage of data. Why wouldn't you have that for Kafka storage? And there's a few things that you'll gain if you do that. Firstly, you're going to get metadata. It's kind of useful for Kafka. You're going to get things like column statistics. You're going to get a different means of partitioning than you're going to get from Kafka, and a whole bunch of other metadata that sits around the data itself. Kafka can find it kind of useful. We have some products at Streambase that use Iceberg metadata to provide really fast seeking and really fast partitioning of data when you want to reload it into Kafka. But it becomes really, really useful when you throw a fully fledged analytical engine at it, like a Spark or a Databricks or a Snowflake. Then you can really start to cook in terms of your data processing. I think it's one of the great missed opportunities in Kafka that we started looking at essentially infinite retention topics, which make perfect sense, but then didn't give developers the tools to be able to access that data in the way that it should be accessed for primarily analytical applications. You also gain the ability to use SQL. Everyone loves SQL. Well, actually, everyone hates SQL, but you can't get away from it. It's been around for 3 decades, and it's going to be 3 more if I have anything to do with it. And finally, you probably already had it. We're talking about standardization previously. Everyone we talk to now is investigating Iceberg. So if it's there, why not use it? It's free. And what we're tending towards is this layout. So the second you start offloading older data from Kafka into Iceberg, you've ended up with this. You've ended up with a shape of a graceful aging of data, a shape of your architecture that looks like a hot set in Kafka that's managing all of your operational concerns and potentially some of your analytical concerns, and a cold set in Iceberg that's providing cheap, highly available, high-volume storage for analytics. This is the dream, and for all of you following along at home, there's been some big moves, mainly by a massive company with a snowflake as its logo, in recent weeks, in order to create this kind of architecture. But immediately you can probably all see there's an availability problem here. What we have is an operational store that's great for serving low latency applications, but cannot access historical data. And the first thing you're going to tell me is, why would Kafka ever need to access historical data? It would, right? There's backfill, there's exceptional scenarios, there's all sorts of reasons why it makes sense to store a large amount of data efficiently in Kafka and give Kafka clients access to it. So if you're a Kafka client application and you want to go back past your 7-day retention, at the moment you've got nothing. You've got the data, it's sat there in Iceberg, but at the moment you've got no chance of accessing it. Similarly, if you have an analytical application, well, you're waiting for that sync time into Iceberg before the data is available to you. So as a data scientist, I want to come along, I want to do some kind of investigation on data that I know we are collecting and should exist, but I have to wait till tomorrow until I can see today's events. So we've built this architecture that could be so potentially powerful, and then we've artificially created technology-only constraints around access to that data. So that sums up long-term storage. We have it, it's possible, Kafka can do it, it would be great if it was in Iceberg. Let's see if we can solve these availability problems. And to do that, I'll hand over to Roman quickly.
Hello. I'll talk about the next piece in the trifecta, write-ahead log. When we talk about write-ahead log, what we mean is the exported write-ahead log, the replication layer from the Kleppmann stock, basically CDC stream or whatever data stream that is used as a buffer for the data is a stream. Basically, if you have, let's say, Debezium CDC connector reading of Postgres, that's what it does. It reads write-ahead log of the Postgres, stores it on the Kafka topic, and it can extend basically availability of that log, stretch it out, so the Postgres itself is not blocked by your replication read. But again, the tier point doesn't disappear at that moment yet. So we have a Kafka write-ahead log here. Data is present there, it's there, but the write into Iceberg only happens when certain thresholds are met, because you're fighting the am I doing a lot of small writes, or I'm buffering, and doing single large write? You're basically fighting the freshness of the data versus optimization of the batch ingestion itself. The Iceberg is not really written to do streaming data ingest. It doesn't handle millions of small writes well. You're paying for it in other ways if you're doing it. You're doing compaction, rewrites, and so on and so on. So again, only data in long-term store still available to the Iceberg clients and readable by them. Nothing in the val that is exported to Kafka is available to them immediately. Now, if we could make that val Iceberg itself without syncing it into Iceberg, if you put a layer that does a cache over the Kafka part of the val and creates on-the-fly conversion to Iceberg. Think about it like a proxy. We have REST proxy for Kafka. Why not Iceberg proxy for Kafka? Yeah? So it can prepare and serve data in memory, do the translation from Avro or JSON or whatever into Parquet, hand it off as an Iceberg to the client without ingesting it into actual S3 or whatever object storage behind the Iceberg table itself. That eliminates both consistency challenges because your source of truth is literally Kafka itself, not a copy of it. And it eliminates that tug of war between what is my freshness versus what is my write cadence. And it's possible in this way. So that's a standard Iceberg layers, just how they would look if you're doing it as a cache in memory in runtime. So you still have your Iceberg catalog, REST catalog that creates table definitions on the fly, reading them from Kafka. So your list tables becomes list topics. Your metadata becomes what the topic structure is. What is my earliest offset, latest offset, multiplied by partitions, and sliced into ranges that are presented as files. Because it's all happening at runtime in memory or on this cache, it's all ephemeral. You're not creating snapshot every time few new messages arrived. You're just going back to Kafka and saying how my snapshot should look like right now for that client that's calling me. Kafka is still source of truth. Everything is there. You don't need to maintain replicated state and so on, because you can always fall back. You're going back to Kafka itself. And the typical flow becomes like this. Your client queries table metadata, the gateway is the REST catalog, queries Kafka for the metadata, returns it, builds a manifest, and the client goes through the S3 or storage endpoint, at which point again the gateway fetches the data from Kafka actively during the query time, not ahead of time, and presents it back to the client of what it is right now. So the last bit, so we have now our valve, the write ahead log, presented as Iceberg, and we still have our actual physical Iceberg sitting there. Now all we need is an overlay that can merge them together into one combined view, because you still have them as two separate things. You have part of your table here and part of your table here. So we can do that again by proxying the actual Iceberg layer, and at the metadata generation, instead of putting the Kafka val part as its own table with its own snapshot, we can proxy the existing Iceberg's metadata and add just one snapshot on top saying, and here is your hotset part on top of whatever you have in your old part. Because the metadata itself has statistics and things, you can read what's the latest tier point, what were the offsets that were copied into it at the last offload, so that you're only serving the part that's actually above it. Because your retention on Kafka might overlap with what you already have in Iceberg. You don't want to duplicate and serve like dual reads and so on. Basically, we're performing union between those data sets now in flight, presenting consistent view between the two. And the impact on Kafka itself is reasonably small, because Kafka is kind of immutable, the data on it is immutable, so we can follow the normal kind of proxy response caching strategy by aggressively caching whatever is being read from Kafka to the analytic clients just on disks, because the cache is pure optimization. If it gets wiped, evicted, whatever, it can always be reread from Kafka, but it removes, like your second time you run the query, you're only reading the delta that is not cached from the Kafka itself. Everything else is sent straight from cache. It has an interesting impact in the sense that right now, for every data source that goes through Kafka, it doesn't have to originate on Kafka. It doesn't have to be an application that writes to Kafka. It's operational stuff. But for every data source that you replicate using Kafka as a transport, all the CDC streams, all that stuff, you have to coordinate creation of it between analytical users and operational platform teams. Because at the platform, you don't know what the downstream users need, and the downstream users don't really know what the upstream applications have. You have that governance and orchestration problem between actual organizational units. I need to access this data. What do you have? What kind of data products or whatnot you have, and so on. And then once you created those pipelines, when do you stop maintaining them? How many of them are no longer used? They were used for a while, now we moved our processes, we don't care about this data anymore, how well it's notified, oh yeah, you can drop it and stuff. This pattern moves that process away from operational team down to analytical ones, because you're just saying, everything you have in Kafka, you can access in the Iceberg, and now your maintenance of it and copying into the long term is literally insert as select. You run it on the analytical side, you're not running a connector, sync connector, or whatever that you stand up on your Kafka cluster or whatever. You're running it on your analytical side as your Spark job, Snowflake job, whatever. So it kind of moves that. I'm the consumer of the data, I have access to all the data, and I manage the cadence of a float, which data I need and which I don't, and so on yourself. Now, if we would do reverse, so that gives us everything as Iceberg. So our analytical clients can read everything as Iceberg. But as Tom said, sometimes you need the same older data as Kafka itself. So you need the reverse, basically. I need to read the Iceberg back into Kafka world for backfills and so on. Again, it's the same thing. You do the Kafka proxy now rather than Iceberg proxy. And inside that Kafka proxy, you're doing the same lookup, but in reverse. Do I have an Iceberg table that matches my topic? What is the boundary of the table? How much I have on the topic? What my earliest offset is there? What is my highest offset in the call set? And do that stitching behind the scene. Because if you've done Avro to Parquet conversion once, your schemas are aligned, everything is there, so you can do Parquet to Avro just the same. And Iceberg is very good at reading at highest throughput. It's not that great at latency itself, at per message latency, but when you're doing backfill, your end-to-end latency is already, you're reading months-old data. There is no such thing as end-to-end latency at that point. You just want to send it as fast as possible so that consumers can read it as fast as possible. And Iceberg is great at that. And with that, I should have said one thing. All of that, where is the back? All of that is only possible because you can view the data as JBob. I'm coining the term. If you've been to my previous talks, you would know. Basically, it's just a bunch of bytes. It doesn't really matter where they sit. Do they sit on Kafka or Iceberg? Given that they're both immutable append-only systems that don't change things in place, we can squint a little bit and manipulate those bytes easily enough to present them in this shape or that shape. Row, columnar storage, hybrid storage systems exist for over decades. So you're doing kind of the same thing. You're ingesting as rows on the Kafka side, you're writing to columns on the Iceberg side, and you just need to have that unified reader that can read columns and project them as that can read rows, project them as columns for Iceberg readers, read columns, project them back as rows for the Kafka readers, have that unified storage architecture going. And with that, I'll give it back to Tom.
Thank you. So we've snuck a few things in there. As you could probably tell, we've solved one of the unhappy faces that we had on our original 4. We've now got some caching involved. We've got a read-through cache that sits up above Kafka and allows us to access our Kafka data as if it was Iceberg. But what we've subtly snuck in at that point is we've changed the semantics of your architecture. So where previously you had to land all of the data into the analytical store before it was available, we've increased that availability. And the way I like to think of it is we've changed from ahead of time semantics, where there is a dependency on movement and a dependency on an ETL flow for data availability, to query time semantics, where when you issue the query, you are guaranteed to get the very latest data available at the point of time that you issued that query. Sounds great, but everything in data infra is a compromise. So we've gained availability. Anyone want to have a guess at what we've lost? Performance. Right. Kafka is not a columnar-based system. It's not meant to fly. It's not meant to be super fast. It's not meant to be super fast for analytics. So we're going to have to do some work in order to make it be competitive with the kind of alternative solutions and make it useful for analytics. If you want to make a database go faster, how do you do it? Oh, come on, it's written on the screen in massive letters. There we go, yeah. Yeah, add an index. I wonder if we could do the same for Kafka. Let's see. First things first, this is my get out of jail free card. Database indexing is a massive field. I am so very far from an expert in this field. In fact, I'm sure there are a lot of people in this room that can run circles around me. Luckily for me, it's pretty much completely non-existent in Kafka. So I only need a basic working knowledge in order to be able to do it. In fact, let's test that basic working knowledge now. Hands up if Kafka has indexes. Got one sort of float, you have to commit. I'm not going with this. I'm not allowing that. Huh? No? 0. That is the first time I've ever had a 0. That's interesting. You are all very, very strongly opinionated and all incorrect. Kafka does, in fact, have indexes, though they are very, very well hidden behind the implementation. If you were to go into the data directories in your Kafka cluster and have a look, the clue is in the name. You will see a file suffix .index in there alongside the actual data segment files. That .index file contains a mapping of Kafka offsets to byte positions within the file. So when you get your consumer and you go, I want to seek to this offset, it'll consult the index and it'll go, okay, I don't need this bit of the file, I can jump straight to here. Similarly, you will find a .time index file. That's exactly the same thing, but I'm looking to seek to a timestamp. And what's interesting about this is you can layer these indexes, and Kafka indeed does. So if you go, I want to consume from 7 o'clock yesterday, what it will do is it will first consult the time index. The time index will give it an offset, and it then will consult the offset index to find a byte position within the file. So these are essentially skip lists that you can layer on top of each other in order to minimize the read. And I'll be very clear, that's all we can do with Kafka. We don't have any, with the public API that's available in Kafka, all we can do is cut down the amount of data we read. We're not going to be able to do any reorganization, any physical mapping or anything like that. So this is our goal. And that's not how we do it today. You'd think what we do is we build a whole bunch of indexes on top of our Kafka data that align to offsets, and that's how we do it. Instead, we do what I call fan-out indexing. If you ever want to query a Kafka topic by a field that's in the value side of the message, what you do is you materialize it somewhere. And I call this fan out because if you take the same topic and you want to query it by a range of different fields, what you're going to do is you're going to do a range of different materializations. If I have a customer's topic that has name, age, and state in it, I'm going to have a materialization by name, age, and state before I can reliably query by filter by name, age, and state with any kind of performance. This keeps me awake at night. This makes me deeply unhappy. Because every time you do that, you're essentially creating an ETL pipeline. And when you create that, you've got duplicated data, you've got tough evolution. I know I said it in a different order. There was a reason, because the main problem you've got is inconsistency. This is glossed over a lot in Kafka, but it's quite bothersome to me. So if each one of these is a separate ETL pipeline that is completely independent of the other one, how do you know that they're all caught up when you're going to query? Let's say I want to be able to, I have an application that queries by name and then queries by age. How do I know the record populations are even nearly the same? I have no guarantees in any way about that. So, Iceberg takes a whole different approach. In Iceberg, we really call this partitioning. It's a very different thing. It's a physical layout, and what we're going to do is we're going to group similar data together so that when we can query, we can choose some filters that are going to make it really, really powerful. So here I've got a bunch of transactions that happen across a number of states. As you can see, all the Utah data is queried together. So when I query for Utah, I drop the other two. Sounds great. It's actually really pretty limited. And if you're transferring Kafka data to Iceberg, really, you may argue with me, and that's fine on this one. But really, you're going to end up with one partitioning key. You're going to be partition offset. It just makes sense. That's what you're going to end up doing. So, again, that doesn't really help us too much. What if we could mix the two? What if we can add a layer on top of our Iceberg data? And when I say Iceberg data, remember everything's Iceberg now. So that also includes our Kafka data. To provide indexing similar to what we have in Kafka. So here we go back to the states. Instead of having having our Iceberg data partitioned by state, it's now partitioned by Kafka offset. But we have these two index layers that sit in the middle. State maps to a bunch of offset ranges. Then offset is the partitioning field in Iceberg. And again, we can prune away all of the data that we don't need. Very nice stuff. And what we've done, again, is made indexes that can be made indexes that are used at query time, not ahead of time. So we've actually subtly solved all of those problems. We no longer have an ETL pipeline. I will talk after if anybody wants to know how you build these indexes, but there is actually no requirement for these indexes to be continually built or for these indexes to be fully populated before they can be used. So we've gained the consistency because they're available across all fields. We've reduced our operational overhead in order to do it, and we've actually gained all of the Iceberg semantics of evolution, which are really, really quite nice. Again, moving ahead of time to query time. That's the central theme. I mentioned before that I didn't have to have a complete index ready before I started to use it. This is because of this concept, the concept of what I call the unindexed head. This only works with numbers, so you're just going to have to work through an example with me on this one. Let's say I have 7,000 offsets sat in a Kafka topic or Iceberg table or spread across a Kafka topic or an Iceberg table. It really doesn't matter for the indexing perspective. I have an index that indexes offset 0 to 5,000. So I've got this little bit at the end. It's a problem, and it's a growing bit because it's constantly being written to, that I don't have any index information for. What should my client do? What should my Iceberg engine or Kafka client do in this situation? Sorry? It could do. We could do that. So that's option one. We can go and we can say, I will hold until the index is complete. I think, is that what you meant? I could say we can hold the query, pause the query until the index is complete and ready. Is that, yeah? So that's option one, and that's the traditional database approach, right? What happens if we just said, oh, well, it's going to make my query perform a little bit worse, but what if we just read it? So we just say, all that not having an index between offset 5,000 and 7,000 means is that you will have to read offset 5,000, 7,000. Okay? So your query will just have to do it. You'll take a performance hit because we're reading data we didn't have to read, but we don't lose anything in completeness, and we don't have any constraints on index state before we can run our queries. This is actually a really nice balance because what you get is a graceful degradation. If your topic is 99% indexed and 1% not, it's going to go really, really fast. If it's 50% indexed, 50% not, it's going to go a lot slower. If it's 10% indexed, 90% not, it's going to go a lot slower. Right? You can choose according to your access pattern and your requirements how you want to play this. So, to sum up about my query time and ahead of time, what do you gain from moving to query time? We've already covered a lot of this, but the first thing you gain is a confidence that your data set is completely up to date. The guarantee that's provided is at the point of query execution or at the point of Kafka client fetch, we know we have the very latest available. We lose a lot of operational overhead. We no longer have to do a whole lot of fan out, a whole lot of ETL. In order to make really technical problems be solved so that we can solve business problems. We get a consistency guarantee. There's no duplication around, so we know we're working with the original data set and we're working with one single data set that everything else is also working with. And And with that single source of truth comes easy evolution. I've got to, if I want to add a column, or if I want to do add a field or change a field type or something like that, I do that once. I don't have to flow it through every single one of my intermediate stores and every single one of my ETL pipelines. Pretty cool, right? And well, the even better bit is Iceberg does most of the heavy lifting for you. So Iceberg was designed with partitioning, column stats, puffin files in there. It's already open, well understood. And like I say, going back to my previous one, you probably already got it, so why not just use it? So let's combine it all together. I've spoken about 4 concepts, and I think we've addressed them all now. We have replication, we have caching, we have indexing, and we have the 4th one that I've forgotten. Materialized views. And they all work together, and we've done it using these 3 mechanisms, using a WAL, including a hot set cache, long-term storage in Iceberg, and indexing over the top of a consistent view that spreads over Kafka and Iceberg. And it looks something like this. At the bottom layer, you retain your existing Kafka and Iceberg for your storage. That's the last thing we want to do, is force a migration into another system. You also, the little sort of half bar just above storage, you also maintain Kafka as your ingestion point. And you maintain Kafka for running your operational workloads. Why not? It's great at it. If you want something that's really caught up and you want something low latency, why reinvent anything other than Kafka? It works great. However, above that, right at the top, I'm going to skip over one and go straight to the serving layer. You have gained availability across analytical and operational applications. You want to bring your consumers, your Flink, your Kafka streams. You can access the full set of historical data that's available across Kafka and Iceberg. Similarly, if you want to bring your application, your analytical applications, your Spark, your Trino, Dremio, Databricks, Snowflake. I always forget to put Databricks and Snowflake on there. You can access that same consistent data set and benefit from the very, very latest data available as if it was Iceberg. And then in the middle, because we've got to make this perform in some way, we have our acceleration techniques. So we're going to aggressively use caching and indexing in order to make sure we can meet the SLAs in terms of performance that we want to do. So, central theme of the talk. We're talking about turning the database inside out. And I'm saying it's more than just materialized views and logs. Right? I'm amazed it's taken us 10 years, but we should look again and see what else we can achieve via these principles. So if you take the principle of unified storage, we're going to get this one consistent view that goes across and is available to all clients. If you add caching to it, you're going to get fast performance and also transparent transforms that just make your data available as if it was something else. And if you add indexing, you're going to get a lot of performance. And the only slide you really need to pay attention to, what this means for your future architectures. You're going to get seamless, real-time, and historical access to data. The seamless is important. There's no longer what we call the ETL wall, where you go, here's my operational data, chuck it over, you care about that. I don't care about what you do on the other side of the wall. This creates a continuous view of your data that goes all the way from the very first data point ever recorded 20 years ago, right the way back to what's happening right now. And there's a subtle governance piece that happens here as well. Because we are talking about continuous data sets, we have an implicit requirement for governance between our operational and analytical data to be consistent, which is a huge win. It's more of an organizational change and another talk, but that's a really important piece. We've also standardized behind de facto standards. We have Kafka and Iceberg. They won. They're everywhere. This is what we want to be using. We've lost a lot of bloat. We lost a lot of ETL. We lost a lot of duplication. We lost a lot of transformation that we were doing for technical only reasons. And we've gained a single source of truth. I just mentioned we have consistent schemas and governance, and a lower operational overhead that goes with it. And I think with that, I am just about done. Or maybe not. One bonus slide. I've got time. I always check. One bonus slide. I said we're doing a lot of making one thing as something else. Well, here we're going to start looking at the transfer of real-time data into batch data as a batch job rather than a continuous job. If you look at this, today you would set up a connector or something like that and you would continuously flow data into Iceberg. You have to, otherwise it's unavailable. And you pay costs, as Roman was mentioning, in terms of small files, metadata explosion, and all of that that go with it. Once you have this consistent view that surfaces Iceberg, you have no requirement to do that transfer. Yeah, you actually have no requirement to do that transfer ever, but you do it when you want to and with as much data as you want to. So if we follow the pattern that I'm going through here, we start off with a large cold set, small hot set, and it's the hot set that's growing. It's just being written. Eventually it gets too big, and we go, okay, at that point, when the hot set is large, and when it's really efficient to move it into Iceberg, we'll just get our nice big fat Iceberg engine that's really good at that to do select star from hot set, insert into cold set, and that big chunk gets moved. And that's it. I can do that in downtime. I can do that at thresholds. I can do that daily, whenever I like. It's turning real time into batch when it wants to be batch, and it's turning batch into real time when it wants to be real time. It's using the right paradigm for when it makes sense and not compromising. And that is the end, I promise. Thanks very much.